Now we solve gate problems related to control unit. Okay. The first gate question. A microprogram control unit is required to generate a total of 25 control signals. Okay. Assume that during any micro instruction, at most 2 control signals are active. Minimum number of bits required in the control word to generate required control signals will be. So the question is about minimum number of bits required to store in the control word to generate this control signals. But at a time, at most 2 control signals are active. Okay. Now I will tell you one question. If the problem is exactly one control signal is active, what we can do I will tell you. Only one control signal. If you don't want to do optimization, answer is directly 25, because what you do is you take a control word with 25 bits. Okay. So whatever, now whether it is one control signal active or anything doesn't matter. If you don't want to save the space, then we can use 25 bits. So this will work for any pattern. Example, let's say 7 control signals are active. They are C1 to C7. Still what I can do is I keep the first 7 bits ones, remaining are zeros. Okay. Example, C1 comma C7 comma C9 are active, remaining are passive, or I can say inactive. Then we can easily represent it, right, with 25 bits. If you want to say that C1, C7, C9 are active, then C1 bit make 1, C7 1, C9 1. All other bits should be zeros in that way. So with 25 bits we can generate. That is what the regular story. But here I have to optimize. Correct? Minimum number of bits are required is the question. Then, so the minimum number of bits, if you want to answer that, what we can do is we can use a decoder and we use only 5 bits. Okay. Let me use only 5 bits and let me generate exactly one control signal out of 25. How I will tell you. Did you remember? If you have a 5 by 32 decoder, what it can do is, so this is your 5-bit control word. Okay. This is your 5-bit control word. So that control word, if you connect here to your decoder, which is 5 by 32 binary decoder. This is called 5 by 32 binary decoder. The property of binary decoder you know, right? So if it is 5 by 32, there will be 32 output lines. Okay, 32. But we don't want 32 output lines. Right? We want only 25. Then what we do is we only select 25. So let us call this is C1, C2, C3, C4 up to C32, right? But I take only up to C25. Remaining I ignore. Okay. Now, how this decoder works is, example, if you represent in your control word 00000, then C1 will be active. If it is 00001, then C2 will be active. If it is 00, that means there are 32 patterns. You should understand that, right? There are 32 patterns. Based on each and every pattern, one of the output line will be active, all others are inactive. If you have this kind of decoder and this kind of circuit, how can we use it? We can use it for generating exactly one of the 25 signals. Correct? Example, you want to only generate C1 signal, then simply represent 00000 in the control word. Right? Now we solved a sub problem. What is that sub problem? Is you have 25 control signals, but out of them exactly one is active at a time, exactly one, right? Then what I can do is I can use 5 by 32 decoder. Okay, so but because we need 25, right? Sir, why don't you go for 4 by something? The 4 by decoder is, see, the model of decoders are generally 4 into 2 power 4 decoder. You will be having 4 into 2 by 4 decoders. Then with that only 4 by 16, you can have only 16 patterns, right? 16 output patterns, otherwise 16 output lines. Then I can generate at most one of the 16 control signals. That's why I don't want that. That's why I'm going for 5 by 32 and I'm using 25 lines. Remaining 7 lines I'm not using. Understand? Now you see how I am going to use it. So my question is, you have 25 control signals and exactly one control signal you have to generate at any time, at any micro instruction. Okay, then what I can do, I can use this 5 by 32 decoder and I use a control word of 5 bit, right? Now example, really I want to activate C4, for that I use a control word like this 0 0 maybe, see, I think 0 1 1 I can use anything, like we can plan it, not a problem. Okay, so that is about decoder. This decoder can be used, but that is not our final problem. What is our final problem? We have a requirement where sometimes, two control signals also should be activated, right? So for that, what we can do is use this kind of decoders too, and use two sets of control words of 5 bits. You see how I do. So these 5 bits you connect to a decoder, okay, so that this decoder structure will be 5 by, let us say, 25, because however the other 7 lines are unnecessary for you, right? Let us use 5 by 25 decoder, and it will create 25 outputs. Okay, each output you can represent as a control signal, right? So now what you do is you plan it such a way that, so whatever use these binary patterns and map them to one of the output lines. That's it. Example, let's say 0 0 0 0 0 may enable C1. 0 0 0 0 1 may enable C2. 0 0 0 1 0 may enable C2, C3. In that way, so all that C25 signals can be planned. Understand? Now, similarly, what I do is I take another word with 5 bits. Okay. Again, I connect them to another decoder. So, what this decoder is going to do is it is going to have 25 output lines again. So, each one I connect to again control signal C1 to C25. Now, according to this decoder property, when you give a input of 5 bits, it will only activate one output signal. Okay, that is traditional decoder. So, if I use the traditional, that is nothing but a binary decoder. The property of binary decoder is each input pattern, for each input pattern, exactly one output will be activated. Now, we can use this kind of output lines for enabling the signals. Now, what is our question? We have a requirement that sometimes we have to enable two control signals, sometimes one, sometimes zero, because at most two. Now I will tell you. Example, you want to enable C7 comma C9. C7 comma C9. What you do is using this set, okay, this binary pattern, plan a pattern such a way that C7 will be enabled. Plan a pattern, okay, plan a pattern so that C9 will be enabled here. In that way, so using these two, we can generate at most two control signals, right? And one more thing, these circuitry, whatever you are taking now, can generate at most two control signals, because here you are getting only one control signal active, here only one control signal. So finally, exactly two control signals will be active, correct? So that is what we can plan. Understand? So finally, 5 plus 5, 10 bits. Using the 10 bits, definitely we can, do this stuff. So if you see the options, 10 is there. But here remember one thing, actual answer is not 10. If you go for a complicated decoder, there are some complicated decoders. How they work, I will teach you in digital, but I just give the rough idea. If you use that complicated decoders, then probably with 9 bits also we can do it. For that, only understand this stuff. Any decoder when you have, okay, it's all about patterns, how many patterns that input can generate. Example, let's say you have 3 input bits A1, A2, A3, then you can realize 8 patterns. Okay, you can plan 8 patterns. You remember at this moment, that's it. Okay, you have 3 inputs, but you want to generate 8 patterns, then we can use 3 by 8 decoder, not a problem. It's all about number of patterns you have. Now we will come to our problem. How many patterns we have? If you see the patterns, we have 25 control signals, correct? Let me write it, C1, C2, C3, so on, C25, right? But they are not random, right? That means they are not randomly getting enabled. So the patterns, if you see, assume that, let's say, at least one control signal should be active, okay? Generally in any machine, for any work, if you want to do some work in the circuitry, at least one control signal should be active. That's why, that is what, general assumption. Okay, that's not a big deal. Let me assume like that. That doesn't change your answer. So if that is the case, at least one control signal should be active. According to our problem, then we can understand our problem like this. At most two control signals means exactly one control signal. Maybe you have to generate exactly two control signals, correct? So what I am telling is exactly zero control signals is not possible, generally not required. Why? You are not generating any control signal, then you can't do any micro operation, right? So to do any micro operation, at least one signal should be activated, correct? That is what the idea. So let me assume that, let's say exactly one control signal or exactly two control signals. That means at most two control signals. So how many, let us come to mathematics. You have 25 signals, okay, C1 to C25. Before minimizing, how many different binary patterns are possible, so that exactly one control signal will be generated. We can do like this. To generate C1 and all others are inactive. This is one pattern. Exactly one control signal active means maybe 1 followed by all 24 zeros, or 0 1 followed by all zeros, in that way. So how many patterns are possible? Now I am coming to patterns. So the number of patterns possible is 25, correct? Where exactly one control signal is active. Now how many patterns, binary patterns are possible which represents exactly two control signals are active? Think about it. Simple. There are 25 positions, right? Take two positions and write ones. In everywhere you write zeros. Then how many ways I can do that? 25 C2 ways. Please attend my combinatorics lectures. In that one, I clearly taught that how many binary numbers are possible with exactly two ones. 25 C2. If you simplify it, you get 25 into 24 by 2, which is 300. Okay. Now, how many binary patterns are possible with exactly one, So they are 25 C1, right? So finally, if you see the total number of patterns, 300 plus 25, 325, correct? Now, these 325 patterns should be generated. For that, how many bits are required? Don't use 25 bits, right? Using 25 bits, you can generate 2 to the power of 25 patterns, but all that patterns are not required. Only few patterns are required. How many? So 325, we can use decoder. So the decoder requires how many inputs, Example, for 16 different patterns, you require 4 by 16 decoder. If you have 4 outputs, then 2 by 4 decoder is required. So if you want to generate 325 outputs, that means 325 different patterns, okay, then exactly what kind of decoder you require, So it will be definitely log 325. Remember the formula. So log 325 is, approximately 9, right? So 9 bits are required. 9 by 512 decoder we can build, so that this can be used for generating 325 patterns. So that's why answer actually 9, okay, but there is no 9 answer, right? So examiner is thinking about a simpler circuit. See, this 9 by 512 circuit will be little bit complicated one, okay, but that 5 by, if you use 5 by 32 2 decoders, then it will be, they will be simple circuits. But this 9 by 325, whatever the circuit, to realize it, it would be little bit complicated. That's why probably he might think like that, okay. Finally, whatever, in the options we have only one suitable answer, which is 10, right, which is near to 9. Example, let's say you thought about, realizing a complicated circuit. So you realize that 9 bits are required, okay. So this 9 is not there here, so go for 10, that's it. Understand? In any way, final answer is C, okay. We'll see second question. An instruction set of a processor has 125 signals, which can be divided into 5 groups, mutually exclusive signals as follows. So that groups are, having mutually exclusive signals. G1, let us say G2, G3, G4, G5. So the question clearly says that this group has some signals. How many? Example, 20 signals. Let us say C1, C2, C3, so on, C20. So that signals are mutually exclusive. If C1 is active, C2 is not active. C2 is active, then C3, C4, all that other signals are not active. So such a group we have with 20 signals. Similarly, another mutually exclusive group we have with how many? 70 signals. Then G3 has 2 signals, G4 has 10 signals, G5 has 23 signals. Then the question is about how many bits of the control words can be saved by using vertical microprogramming over horizontal microprogramming. Let us calculate total number of bits required if you use vertical programming. Okay. So in vertical microprogramming, since out of 20, exactly one is active at a time, then you don't require 20 different signals or 20 bits, right? We require only log 20 bits, correct? We know that. We can use decoder and we can generate 20 patterns using 5 by 32 decoder, right? So that's why only 5 input bits are required. 5 here. Now blindly apply from now onwards log formula. Log 70. Log 70 is 7 bits, right? So with 6 bits only 64 patterns we can generate. We have 70 signals. That's why log 70 is what? 6. Now out of 2 only 1 should be generated. That's why 1 bit is required. Now here 10. Log 10 is 4, correct? So now log 23. So 32 we have to use. That means 5 bits. So finally 5 plus 6 plus 1 plus 4 plus 5. 9, 10, 16, 21. So 21 bits are required actually. So what is the save? The question is about, so let us revise. For 20, how many bits are required? 5 plus 70. How many bits are required? 7 bits. For 2, 1 bit. For 10, 4 bits. For 23, 5 bits. 5, 9, 10, 16, 21. Remember. So 12, 13, 17, 22. Sorry. 5, 7, 12, 13, 17, 22. So finally 22 bits are required. But the question is not about how many bits are required. How many bits of the control words can be saved? So to know the saving, first you should know the number of bits required in horizontal microprogramming. In horizontal microprogramming, every bit will have every signal will have one bit. 125 signals, 125 bits. Then 125 minus 22 is the save, right? So finally, how many bits we saved? Almost 123. Sorry, 125 minus 22, 103. So 103 bits we can save. Option B is the right choice. In that way, easily we can answer this question. Okay, understand the concept so that any gate question you can answer related to this kind of microprogramming problems. Okay, let us see this question, which is asked in GATE 2013. Consider the following sequence of micro operations. They have given some micro operations. If you see here, memory buffer register, memory address register, they are using, right? These two. Sir, you never taught us what is memory address register and memory buffer register. I will explain you. So the question is about which one of the following is a possible operation performed by this sequence. So before going to the problem, I will explain you what is this memory address register. Okay, and sometimes people use memory data register and memory buffer register. Okay, so this I'll explain you what is memory address register, memory data register. Even memory buffer register is not required for this problem. Generally, you have, let's say, this main memory. This is your program counter, and your memory is designed such a way that there will be memory address register and memory data register. And whenever you specify some address in memory address register, like example, program counter shows 100. If you transfer that 100 here, okay, then if you initiate read operation, then what is going to happen is, so your memory interface will be designed such a way that it will understand that address is 100, and that interface will be designed such a way that exactly that memory address 100 will be enabled, that will be taken. Now the data will be transferred to memory data register. Such a way generally architectures will be designed. So what is the purpose of memory address register? To specify the address to whenever you wanted to access the data. Right. What is memory data register? Why we require it? Whenever you want to, once you specify the address, you have to store the data into some register, right? From memory, we have to transfer that to our temporary registers or general purpose registers. So memory data register might be one of the general purpose register onto which we are going to take the data. But in my lectures I have not used, okay, but I didn't get, so I never needed it. But some of the architectures generally use memory address register, memory data register. This is enough, okay. If you understand this one, then probably you can answer any gate question. Now we'll come to our problem. In the problem, 4 operations are given, micro operations, right? 1, 2, 3, 4. You know what is micro operation, of course. Set of micro operations will form an instruction, right? So now which one of the following is a possible operation performed by the sequence? Now let us observe this first instruction or micro operation. What is happening here? There is a memory buffer register. Let's say MBR is one register. Doesn't matter for you what it is. Generally it is used for temporary storage. So you are storing program counters value into memory buffer register. Okay, if it is example 100, we know generally program counter always points to the current instruction which is going to be executed or next instruction, depends on the situation, correct? So program counter, let's say at this moment, is pointing to the next instruction, instruction to be executed. Okay, so that you are copying into memory buffer register here. I don't know why. That is what we have to find out. After that, x is not mentioned. X and y are two variables. They did not talk about what is x, what is y. But x is moved to memory address register. Y is moved to PC. Then after that, see this one. Memory, that means your memory, main memory. So memory, assume that let's say some memory location where you are storing this data, which is stored in memory buffer register. So initially you stored something in memory buffer register, right? That you are storing in finally memory. Finally you are storing some program counter value, otherwise current address, into memory. Remember it. Generally, why you do that? Do you do that in fetch, or do you do that in operand fetch? Do you do that in conditional branch, or do you do that in initiation of interrupt service? Definitely we do that in initiation of interrupt service. You are storing the program counters value in memory means what? Definitely. So we have to come back. Generally, why we store the current instructions address? To come back. Maybe why you want to come back? Reason is maybe it's a function call. Second one, probably this is a interrupt, right? Example, let's say you are executing one instruction. Suddenly if interrupt comes, then what you do? Now recall, already I explained you. Then we store the current address in memory. Then after that we will service that interrupt, then we'll come back, right? So that's why definitely this set of operations should match, otherwise are required for initiation of interrupt service, right? So option D is the right answer, and A, B, C are not at all competitors, right? So we never do storing the program, we never store the program counter in the memory for fetching the instruction or fetching the operand. If you want to fetch the operand, go and fetch the operand. Why you want to store program counter, right? We never need it. That's why by seeing the options quickly we can eliminate, and we can say that this is the right answer, right? Without knowing what is x, what is y. X and y are some of the arguments in your instruction, doesn't matter. Don't worry about them. Understand? In that way, very quickly sometimes we can answer the questions. We'll see this gate question. So in this gate question, finally we have to find out number of bits required for x, number of bits required for y, and size of the control memory. Okay. Now, sir, how to understand this circuit in the gate exam? So it is really not required to understand this circuit completely. Okay, we can solve this question very easily, because the objective is finding x value, y value, control memory, right? Let us solve the problem like that. After that, I will explain you what is the meaning of this circuit. Okay, of course, you might have understood already some of the parts of this circuit. Okay, but clearly I'll explain why each and every device are, this multiplexer and why this each and every circuit is required. Let us start solving this problem without understanding much. The question is directly XY control memory size, right? So let me directly focus on this one. Control memory is divided into three parts. One is Y, one is X, one is 13. So finally X plus Y plus 13 is the size of the each control word, right? In a control word there are these many bits, X plus Y plus 13. But already in the question they have mentioned that the number of control bits are 26, right? That means the control word size is 26 bits. So x plus y plus 13 is 26. Then x plus y equal to 13, right? Because overall is 26. So x plus y 13 should be the one thing you should understand. So 10 plus 3 13, you see, this is x, this is y. 10 plus 3 13, 8 plus 5 13, 5 plus 8 13, 10 plus 3 13. So with this information you are not able to eliminate any of the options. We'll still try. If you see this multiplexer has 8 status bits. I don't know why they are required, but they have given. To control that status bits, those we are using select lines, okay? So, how many bits are required to select one of the line from 8? We know that generally to select one of the 8 lines, you require 3 by 8 multiplexer, correct? So, that's why 3 bits are required here. We know that, right? So y value is decided, that is 3. Directly go to the options. Y value should be 3, correct? So either option A or option D. Now 10, 3, 1024, 10, 3, 512. Which one? It depends on size of the control memory. Now we will come to size of the control memory. So this control memory size depends on the address of the control memory, correct? So here this control memory is addressed by this control address register. So how many bits are there in this control address register is important. If you see here, that control address register is sometimes loaded by this word, right? This field. What is that? X. So what is X value? Already we know X value here 10, correct? If X value is 10, then control address register size is 10. If the control address register size is 10, then how many distinct memory locations it can address? 2 to the power of 10, correct? We know that control memory is word addressable, right? Every word we number. Then how many words are there in control memory? 2 to the power of 10. That's why I can say size of the control memory, which is nothing but number of words in this control memory, equal to 1024. That's it. So answer is A directly. So we can easily answer this question without knowing much about this circuit. But now we'll try to understand what is this circuit. Very simple. So you know, in microprogramming, when you have control memory, so that control memory will have some set of control words, correct? Control words. So some bits will go for, you know, micro operations. That means they generate control signals, correct? Fine. Now remaining bits are going to decide the next address, correct? Next address. In this one also, the remaining bits are deciding the next address. How? You see. So one field directly connected to the next address, right? Control address register always points to next address. That's why. So this Y is, this X is connected to directly next address. That means X is deciding the next address. So what is this Y, sir? It is not always next address. That means once you take control word and once you generate the signals, the next time it is not always to take the next address here. Sometimes we have to depend on other environment. Already I told you. Generally, why you sometimes want to jump to another address? Think about it. Maybe some of the processor status bits, you know, are going to affect the flow of the execution of the instruction, correct? That's why. So this multiplexer is having some status bits. So based on the status bits, now sometimes what happens is your control address register is modified. You see, this multiplexer is connected such a way that some lines are connected to load, some lines are connected to increment. That means, you know, whatever the status bit is selected here, that is going to affect this control address register in two ways. Sometimes load, sometimes increment. Okay. So forget about, you know, which one is affecting in what model, doesn't matter for us. But sometimes your status bits are deciding that we have to go for load, sometimes increment. Sir, what is load? Whenever you can understand like this, whenever there is a load bit enabled, that means what? We are loading this control address register by the next address. Maybe this address we are loading. Fine. Sometimes we are not loading this address, but we are incrementing the current control address register. You know that, right? So did you remember when you have control memory? So how you execute that operations, like micro operations? So we take each and every control word sequentially, because control memory also, it's a micro program, correct? Control memory also has micro program. Sometimes we take sequential addresses, suddenly we jump. Now the question, whether to jump or increment will decided by this multiplexer, correct? See, some status bits says that load, that means directly go to jump. Now some status bits say that go to increment. In that way it is planned. You see, especially why this complementation I will tell you. Example, let's say one of the status bits, when it is selected, it is having, you know, voltage value 1. just possibility. Example, one of the select bit is 1. So that one, if it goes like this, then that will enable load. This one goes like this, one will become what after complementation? 0. Then this will disable this incrementation line. So finally either loading is happening, otherwise incrementation. That is the way this complementation is working, right? So this is about all the circuit. Finally multiplexer does what? It will either load the register next address, otherwise it will increment the current address, right? So this is about control memories design. Doesn't matter for us, but to solve this problem just you need a basic idea, not in details, right? That is about this problem. See this question. In this question we have to find out equation for S5, equation for S10. That means when to assert signal 5, when to assert signal for S10. Okay, we will see. If you see the table, you understand that in the T1, T2, T3, T4, T5 are time periods, correct? First clock cycle, second clock cycle, third stage, I can say. This is the fourth clock cycle, also fourth stage in that way. So this is fifth clock cycle. So this will be repeated, right? So instruction 1 requires S5 signal in this period, time 1, right? Similarly, if you see instruction 2 also wants, I3 also needs this S5 signal, I4 also needs S5 signal. That's why S5 is required for every instruction. So that's why what we have to do is, so at T1 we have to generate S5 signal always. That's why this equation you see, S5 equal to the equation for S5, because we are going to design a circuit. This is hardwired control unit. So to design a circuit for S5, then the equation will be like this for T1 every time, right? For every instruction. In the T2, T3 cycle, you see, and just identify S5. Do you see S5 anywhere in T2? In T2 there is no S5. In the time period T3, do you require S5 for anything? Yes, I2. That means now by seeing this one, I can write the equation directly without seeing the options. See, entire T1, the signal should be active, and where that signal should be active? In other places, if you see in T3, right? T3 and the what for which instruction? I2, right? So T3 dot I2. See here, S5 for, S5 is active for I4 also. That's why T3 I4. I can say T3 into I2 plus I4 I can write, correct? In that way. So it's very easy problem. We have to just assert where is that S5. Next, anything else? No S5, no S5. Finally, answer is for S5, T1 plus T3 into I2 plus I4. T1 plus I2 plus I4 T3. This might be the answer. See, T1 plus I2 plus I4 into T3. Yes, this might be the answer. T1 plus I2 plus I4 into T3. So this might be the answer, but this one cannot be the answer. Option A is eliminated. Now, similarly, we have to write the equation for S10. So just check. Is there any S10 in T1 line? No, that's why. So for S10 equation, there should not be T1, right? Now if you see the options, so T4 into something plus T5 into something, T4 into something, T5 into something. Here it is T2 into something plus T4 something, T5 something. It is T2 into something plus T3, T4, T5. So now what we do is we just see timeline 2, T2. In this T2, S10 active or not? Yes. Where? In I2 and I3. That's why I can say that I2 plus I3 into T2, right? The signal S10 is active at I2 and T2 plus I3 into T2. Correct. That is what I realized. So in the options, we should have I2 dot T2 plus I3 dot T2. Well, let us check it. So if you see here options, this cannot be the, of course already this cannot be the answer. Now we'll see option B. In option B, so we should have I2 T2, but there is nothing like that, right? There is no signal T2. There is no time T2. So either this one or this one. Now T2 into I2 plus I3 only. But here if you see it is I2 plus I3 plus I4. In instruction 4, do we require in the T2 timeline, do we require S10? No. See, I4, T2, there is no S10. But here you see, he is unnecessarily generating a circuit such a way that that circuit is going to generate a signal, S10 signal for this case also. What is that? I4 into T2. That is wrong. That's why directly I can say that S10 is nothing but this one, because all other options are eliminated. Let us check one more time. Let us write completely. Now we have confidence how to write equation, right? Go to directly S10, because we have to write an equation for S10. You see here, nothing here for 2 instructions. That's why I2 plus I3 into, what is the time period? T2 plus, in the T3 line only I4. That means I4 into T3 plus, in this line I1, I3. So I1 plus I3 into T4 plus T5 into, see, for T5 I2 plus I4, I2 plus I4 into T5. That should be the answer. Let us check. I2 plus I4 T5 correct, I1 plus I3 into T4 correct, I4 T3 correct, I2 plus I3 into T2 perfect. So option D is the right choice. In that way easily we can answer questions related to control unit. Okay.